We're going to take a look at a few more types of problems that you might have to work on related to intermolecular forces. And on these, we're going to be looking at mixtures, so you can see mixing, or actually not mixing, but comparing different compounds. And then on the next page, we'll see some mixtures. So as I look at these problems, we're going to compare the pair of molecules. We're going to use intermolecular forces and or size to predict which one in each pair has the higher boiling point. So high boiling points, just to remind you, are going to be substances that look like solids or liquids at room temperature. In other words, these molecules are sticking together really well, and then in a gas, those are low boiling points. They already boiled and the molecules aren't really sticking together so well. So to think through this boiling point, you really have to go through a few steps, okay? And this is why these problems are deceivingly simple looking, but you really have to put some thought into them. So first of all, is each molecule polar? And you may have to sketch out some of the structures, or you might start to just know them. But carbon dioxide, remember we had seen, was nonpolar, and water, you should start to know always is polar. So water's polar, carbon dioxide is not. I might write a little nonpolar, polar. So that's my first question. Then I want to think about which intermolecular forces can these participate in. If I've got a bunch of carbon dioxides, how can they be attracted to each other? So now you're going to bring back your sheet with all the intermolecular forces. For carbon dioxide, it's nonpolar. So molecules that are nonpolar have one option for attractions to each other. Those are London dispersion forces. So my carbon dioxide, I know, only is going to have dispersion forces. If I look at a sample of water, so this would be if I have a bunch of waters together, what is the strongest type of attraction I can have? Water, we've got this OH, so we have hydrogen bonding, right? And if I have hydrogen bonding, I also have dipole-dipole and dispersion forces. So I can say that between two water molecules, I have dispersion, dipole-dipole, and H bonding. So if I'm comparing a sample of carbon dioxide and a sample of water, and I want to think about which one's going to be easier to boil or easier to tear those molecules apart, I look at the carbon dioxide and I say carbon dioxide is going to be very easy to tear apart, and so higher boiling point, I would say water has the higher boiling point, BP, because it has stronger IMFs. Or I sometimes think about those molecules, H2Os, being very sticky when they're next to each other, or like strong Velcro, okay? So first, polar, nonpolar, helped me think through the IMFs. Which IMFs are the strongest? If it has strong IMFs, it's gonna have a high boiling point. Let's take a look at a second example, and then we'll leave a bunch for you to think through on your own later. So let's look at CH4 and C6H14. First question, is each molecule polar? All C's and H's, so if they're all C's and H's, I know that these are both nonpolar, all right? If they're nonpolar, which type of intermolecular force can I have? Only these nonpolar molecules have dispersion forces, right? Or sorry, nonpolar molecules only have dispersion forces. So these are both dispersion, and that's it. All right, so now we have this tie. We're like, well, I'm not very sticky and you're not very sticky. So how do we tell the difference? This is where we look at size, and it helps me to think about if I throw things into the dryer again and I have these random collisions. If I throw something big in, like a big giant blanket, it is definitely going to stick to other things because it's big. If I throw little socks in, they're not necessarily going to stick to anything because they're small. And so when we think about stickiness, the bigger it is, the more sticky or the more attracted it will be to other things, okay? So when you are big, I'm going to say here, C6H14 has the higher boiling point because it is big, and I'm literally just counting atoms here, even comparing one carbon to 6, the carbons being very important here in terms of size. We'll learn about mass in the next chapter, and we could use mass too to say this has a higher mass. So C6H14 has the higher boiling point because it is big. It will attract molecules more strongly. Just like something big in the dryer will stick to other things. So that is looking at the boiling points, and you've got some more to think through. Next column says compare the molecules, it's the same pairs, and say which one is likely to be a gas at room temperature. So here, when I look at high boiling point, I was thinking strong intermolecular forces and or big molecules. When I look at a gas, look at the gas over here. The gas is not going to have very strong attractions between particles, right? So the gas is going to have relatively weak IMFs and or be small. So if I look at CO2 and H2O, here we had seen that CO2 has very weak attractions. That's going to be a gas at room temperature. CO2 is more likely to be a gas because it only has dispersion forces. Okay, so a gas is the opposite of a high boiling point. A gas is a very low boiling point, is another way to say that. Let's take a look at these two. So this was methane and hexane. This is what comes out of your stove, the gas, and this is the liquid gasoline that goes into your car. So which one of these is more likely to be a gas? Well, gas is going to have weak attractions and or be small. And if I look at these two, here's my weaker attractions because it's small. So CH4 is a gas because it is smaller than the other one. All right, so that's kind of how I think through those. I might ask you about boiling point. I might ask you about gas. Either way, you want to go through this same thought process here.